Hi, welcome to the ComSci 137 lecture. Sunny here. In this module, we will discuss switching. Let's start. A network is a set of connected devices. Whenever we have multiple devices, we have the problem of how to connect them to make one-to-one communication possible. One solution is to make a point-to-point connection between each pair of devices or between a central device and every other device. These methods, however, are impractical and wasteful when applied to a very large network. The number and length of the links require too much infrastructure to be cost efficient, and the majority of those links would be idle most of the time. Other topologies employing multi-point connections, such as a bus, are ruled out because the distances between devices and the total number of devices increase beyond the capacities of the media and equipment. A better solution is switching. A switch network consists of a series of interlinked nodes called switches. Switches are devices capable of creating temporary connections between two or more devices linked to the switch. In a switch network, some of these nodes are connected to the end systems. Others are used only for routing. Traditionally, three methods of switching have been discussed: circuit switching, packet switching, and message switching. The first two are commonly used today. The third has been phased out in general communications but still has networking applications. Packet switching can further be divided into two subcategories: virtual circuit approach and datagram approach. Switching can happen at several layers of the TCP/IP protocol suite. At the physical layer, we can only have circuit switching. There are no packets exchanged at the physical layer. The switches at the physical layer allow signals to travel in one path or another. At the data link layer, we can have packet switching. However, the term packet in this case means frames or cells. Packet switching at the data link layer is normally done using a virtual circuit approach. At the network layer, we can have packet switching. In this case, either a virtual circuit approach or the datagram approach can be used. Currently, the internet uses a datagram approach, but the tendency is to move to a virtual circuit approach. At the application layer, we can only have message switching. The communication at the application layer occurs by exchanging messages. A circuit switch network consists of a set of switches connected by physical links. Connection between two stations is a dedicated path made up of one or more links. However, each connection uses only one dedicated channel on each link. Each link is normally divided into n channels by using FDM or TDM. It has three phases: connection setup, data transfer, and connection teardown. It is efficient, and some dedicated lines can be unused. It has minimal delay. This figure shows a trivial circuit switch network with 4 switches and 4 links. Each link is divided into 3 channels by using FDM or TDM. As mentioned, circuit switching takes place at the physical layer. Resources like bandwidth in FDM and time slot in TDM, switch buffer, the switch processing time, and the switch I/O ports must be reserved. Data transfers are in a continuous flow. No other thing is involved in data transfer. Delay is minimal in circuit switch network. Before the two parties can communicate, a dedicated circuit needs to be established. During data transfer, the data are not delayed at each switch. The resources are allocated for the duration of the connection. In packet switch networks, messages are divided into packets of fixed or variable size. The size of the packet is determined by the network and the governing protocol. In packet switching, there is no resource allocation for a packet. This means that there is no reserved bandwidth on the links, and there is no scheduled processing time for each packet. Resources are allocated on demand. The allocation is done on a first-come, first-served basis. When a switch receives a packet, no matter what the source or destination is, the packet must wait if there are other packets being processed. We can have two types of packet switch networks: datagram networks and virtual circuit networks. In a datagram network, each packet is treated independently of all others. Even if a packet is a part of a multi-packet transmission, the network treats it as though it existed alone. Packets in this approach are referred to as datagrams. Datagram switching is normally done at the network layer. Datagrams may arrive out of order or get lost. It is connectionless. No information on state of connection is saved. There are no setup or teardown phases. Each packet is treated the same by a switch regardless of its source or destination. If there are no setup or teardown phases, how are the packets routed to their destinations in a datagram network? In this type of network, each switch has a routing table which is based on the destination address. The routing tables are dynamic and are updated periodically. The destination addresses and the corresponding forwarding output ports are recorded in the tables. Headers contains address. The destination address in the header of a packet in a datagram network remains the same during the entire journey of the packet. The efficiency of a datagram network is better than that of a circuit switch network. Resources are allocated only when there are packets to be transferred. However, there may be greater delay in a datagram network than in a virtual circuit network. Although there are no setup and teardown phases, each packet may experience a wait at a switch before it is forwarded. In addition, since not all packets in a message necessarily travel to the same switches, the delay is not uniform for the packets of a message. A virtual circuit network is a cross between a circuit switch network and a datagram network. It has some characteristics of both. As a circuit switch network, there are setup and teardown phases in addition to the data transfer phase. Resources can be allocated during the setup phase, as in a circuit switch network, or on demand, as in a datagram network. As in a datagram network, data are packetized and each packet carries an address in the header. However, the address in the header has local jurisdiction. As in a circuit switch network, all packets follow the same path established during the connection. A virtual circuit network is normally implemented in the data link layer, while a circuit switch network is implemented in the physical layer, and a datagram network in the network layer. But this may change in the future. In a virtual circuit network, two types of addressing are involved: global and local. A source or a destination needs to have a global address, an address that can be unique in the scope of the network, or internationally if the network is part of an international network. A global address in a virtual circuit network is used only to create a virtual circuit identifier. A virtual circuit identifier is the identifier that is actually used for data transfer. It is a small number that has only switch scope. It is used by a frame between two switches. When a frame arrives at a switch, it has a VCI. When it leaves, it has a different VCI. To transfer a frame from a source to its destination, all switches need to have a table entry for this virtual circuit. The table, in its simplest form, has 4 columns. This means that the switch holds 4 pieces of information for each virtual circuit that is already set up. In the setup phase, a switch creates an entry for a virtual circuit. 2 steps are required: the setup request and the acknowledgement. In the setup request, a setup request frame is sent from the source to the destination. The switch acts as a packet switch. At the acknowledgement step, a special frame completes the entries in the switching table. In a virtual circuit network, all packets belonging to the same source and destination travel the same path but may arrive at the destination with different delays if resource allocation is on demand. If resource allocation is on demand, the source can check the availability of the sources without actually reserving it. In a virtual circuit network, there is a one-time delay for setup and a one-time delay for teardown. If resources are allocated during the setup phase, there is no wait time for individual packets. Circuit switching today can use either of two technologies: the space division switch or time division switch. In space division switching, the paths in the circuit are separated from one another spatially. This technology was originally designed for use in analog networks but is currently used both in analog and digital networks. It has evolved through a long history of many designs. Crossbar switches and multi-stage switches are used in space division switching. Time division switching uses time division multiplexing inside the switch. The most popular technology is called the time slot interchange or TSI. We can combine space division and time division technologies to take advantage of the best of both. Multi-stage switches of this sort can be designed as time-space-time switches. A crossbar switch connects N inputs to M outputs in a grid using electronic microswitches at each crosspoint. The major limitation of this design is the number of crosspoints required. To connect N inputs to M outputs using a crossbar switch requires N times N crosspoints. For example, to connect 1000 inputs to 1000 outputs require a switch with 1 million crosspoints. This is impractical. The solution to the limitations of the crossbar switch is a multi-stage switch, which combines crossbar switches in several stages. In a single crossbar switch, only one row or column is active for any connection, so we need n by n crosspoints. If we can allow multiple paths inside the switch, we can decrease the number of crosspoints. Each crosspoint in the middle stage can be accessed by multiple crosspoints in the first or third stage. This figure combines a TDM multiplexer, a TDM demultiplexer, and a TSI, which consists of random access memory with several memory locations. The size of each location is the same as the size of a single time slot. The number of locations is the same as the number of inputs. The RAM fills up with incoming data from time slots in the order received. Slots are then sent out in an order based on the decision of a control unit. We combine space division and time division technologies to take advantage of the best of both, combining the two results in switches that are optimized both physically and temporally. Multi-stage switches of this sort can be designed as space-time-space switches. A packet switch has four components: input ports, which performs the physical and data link functions; output ports, which performs the same functions as input ports in reverse order; routing processor, which performs functions of the network layer; and a switching fabric, which can be a crossbar, a banyan, or a Butcher-Banyan switch. A banyan switch is a multi-stage switch with microswitches at each stage that route the packets based on the output port represented as a binary string. Here is an example. In this figure, input 1 is sending a cell to output 6. 6 is 110 in binary. Input 1 goes to 1, then 1, then 0 to reach 6. This figure, input 5 is sending a cell to output 2. 2 is 010 using 3 bits. Input 5 goes to 0, goes to 1, then goes to 0 to reach 2. However, there is a possibility of internal collision even when two packets are not heading for the same output port. This is solved using a Butcher-Banyan switch, a combination of Banyan switch and a switch designed by K.E. Butcher, which sorts incoming packets according to their final destinations. This ends Module 11. Thank you.